All right, folks, I will get started. Last time, which was 2 days ago, we talked about what is generative AI. If you recall, we talked that it has a long history. It has become the buzzword in 2023. People often consider it synonymous with large language models. But it turns out, and I hope I did give you a convincing history of this subject, that made you feel that it has been there for a very, very long time, since 1980s. Machine learning has had two parts, the discriminative and the generative. I mean, amongst other things, it has reinforcement learning and so on and so forth. But this generative has been there for quite as long as discriminative machine learning has been there. Though in broad usage, generative is always a little bit harder. And so it took a while to find its stride. Now, for the last decade, it has had quite a dominant influence on the field of AI. Today, I would like to go into one of the earliest generative AI models. And the reason I'm going into it is it's simple to understand because I want to give you folks a flavor of the technology behind it, the neural architecture behind it. So I will be writing some things on the board and explaining it, and then I'll show it to you in action. I hope that this will be a fun exercise. So this is an architecture that came out in 2014, almost a decade ago. This started out from an idea which has been there in in pretty much artificial intelligence. It's a kind of algorithm that is called min-max, where one thing tries to minimize an objective function or a goal, and the other agent tries to maximize it. And the best way to explain this min-max idea and how it relates to generative AI is to start with a sort of example. Imagine that you have a counterfeiter, somebody who counterfeits the US dollar, let's say. And so we will take a person. This is the counterfeit, the counterfeiter. What the counterfeiter does is takes just a random input, a random trigger. It doesn't matter what. And every time it produces a new currency. Let us say it produces a new currency. And I'm writing it as this Z is just a random trigger because it wants to, on a whim, produce a new kind of currency. It produces a currency. Let's say that it looks like a dollar bill. Right? There you go. Something like a dollar bill with 100 written on it. It produces something like this. This is the this is the output that it produces. Now, people often call this the generator because it is generating fakes, a generator of fakes. And now imagine that obviously if the generator is too good, if the counterfeiter is too good, the markets would be saturated with fake currency, and obviously you can take down the economy in effect, or you could then everybody would start doing that. The reason you don't see too many counterfeits in the market is because obviously because you have a cop. Imagine a cop here or expert here who can take a counterfeit, right? And this counterfeit is, let me just call it, actually, I wrote it as X, let me just call it, given this, and this will produce a Z of some random input. It will produce a counterfeit GZ. Think of it as a function. I give it noise, some random value. And it manages to produce a counterfeit. And every time it produces, it looks slightly different. Now, why would it like to produce a slightly different counterfeit? And here is where it gets tough. It turns out that the counterfeiter The crook has no idea whatsoever what the US dollar bill looks like. Let's say that the person has never seen a US dollar bill. And so in the beginning, what the counterfeiter might do is, or the crook might do is, it may draw a, like a, I don't know, a bird and say, here is my $100 bill. And the cop will look at this and say, haha, this is wrong. Right? But the next time, the generator will produce a different sample because the generator has absolutely no idea what a counterfeit bill looks like, what a genuine US dollar bill looks like. And so the cop will say, no, this is not what it is. But then the question is, how good is the cop and how does the cop learn? Now, what you do is, you imagine that you have a pile of real, a pile of real dollar bills. And so what happens is, every once in a while, randomly, you either feed it real data, a sample, an example of the real data, or you feed it an example of a counterfeit data. And the cop has to tell whether it was real or it was fake. The expert has to tell that. And in a way, the expert is also learning, but the expert has an advantage. Expert is told the answer. Expert is told that, hey, I gave you this. What did you predict it to be? Let's say that it predicts it to be real. So then you say that was right because it was actually real. You make predictions wear a hat in this field of AI. So you suppose it was real, and then you say, oh yes, it was real. So now what would the expert do? It will say, oh, that is what a real bill looks like. Now, suppose it gets a counterfeit and it says real. Accidentally, it says real, and that would be a mistake because it was a fake, right? And so the expert realizes that it made a mistake. What the expert produces in a more technical jargon is probability of real dollar bill. So what should happen? For this case, for the case one, probability of real should be close to 100%, should be close to, should be. This is the should be part. Should be. And according to, if the expert has learned, then the probability that it should assign to a fake bill should be approximately 0% probability. Does that look like common sense, guys? That you should say a good expert should assign. See, there's always an element of lack of surety to it, but it should do that. But what happens if it makes a mistake? And this is the beauty of AI. The intelligence part that we talk about in artificial intelligence comes from the fact that machines can learn. See, you call a human being intelligent if the human being is a quick learner. In the same way, machines, the intelligence in a machine is its ability to learn from data. So when you tell it that it made a mistake, in the more technical jargon, you say that there is something called a loss. Loss is a measure of how wrong it was. How loss function. People often use the word quite often, and you'll see it often, and you'll see it used in the literature, the loss function. Loss function is how overall how wrong was this expert. And when this expert is often called the discriminator because it discriminates between the real and the fake. So the discriminator of the loss function of the discriminator, what you want to do is, if it is very good, then the loss would be less. On the other hand, in the beginning, let's say that the expert or the discriminator is also not trained. Then what would happen is the loss would be high. It would make a lot of mistakes. And when it makes a lot of mistakes, then comes the question, how do you teach it? By showing it the real answer, the loss will tell you how wrong you were. And then comes the magical part that makes all of machine learning effectively, or much of machine learning possible, what happens is that you can do something called a gradient descent. The discriminator has lots of weights, and the neural networks is made up of lots of parameters inside it. Those are weights, those are knobs. One easy way to think about it is that the discriminator has lots of knobs, and as the signal goes through, it makes a prediction. But if you turn the knobs, then the prediction will change. And now what happens is any one parameter, which is sometimes called the weight, you can update the weight from the previous value by doing something called a gradient descent step. And I won't get into that. It's called a gradient step. Now, that's quite a mouthful. And since some of you are a non-technical audience here, I would suggest don't at this moment pay too much attention to it, except to remember one fact. All machine learning algorithms, a large class of them, there are two ways. Once you can learn by reinforcement learning, punishment and reward, but the other class of machine learning algorithms, they learn through a process of, or predictive models, they learn to think, in some sense, form a conception or a function of the what the data is trying to say by minimizing the loss. And when you try to minimize the loss, there is a very efficient way to go about decreasing your loss and therefore learning at the fastest way possible. And that way is called gradient descent. The gradient word, this inverted triangle, it is basically very similar to derivative. What in one variable you would call derivative or derivation of a function. It's a derivation of a function if the function is made up of many, many, many parameters or variables. So this is the celebrated gradient descent equation, but I won't go into that. Suffice is to say that if you can quantify how wrong the discriminator was, how wrong the cop is, you can do something about it. You can turn the knobs inside the cop in such a way that now the cop, in the next time around, you show the cop the same dollar bill and it will say, this is real. And if you show it a fake dollar bill, it will say a little bit less likely to be wrong. It will still be wrong quite a bit, but it will be a little less wrong. And that is one little step of learning that the discriminator has gone through. Now think in terms of the generator. If the discriminator knows that this was a fake, the generator would say, oops, that didn't fly. So what can I do? Maybe with this bird, I can remove the tail. Let's see what happens if I make small changes to it. Or let me generate another dollar bill. I have no idea what dollar bills look like, but let me generate something slightly different. Right? I have a certain conceptualization. Maybe my concept of a dollar bill is it has a bird on it, but let me make it a little bit less bird-like. Make small changes to it, and then try to push it, and then see what happens. And let's say that if the discriminator is a little bit less sure, it says, well, no, this is not obviously a fake, but maybe it is a fake. It very probably is a fake. Now the generator has had a tiniest bit of a win. The generator says, that's good. It means it's moving in the right direction. Right? It will do more of the changes that will confuse the cop. And even though it has never seen a real dollar bill, by making small adjustments and just observing, what did the discriminator think about it? What did the cop think about it? You just want the cop to be a little less sure till you finally want, your end goal is as a counterfeiter, as a fake dollar bill generator, to completely confuse the expert, completely confuse the cop. So if the cop is totally not sure, or better still, is quite sure that what you produced is a genuine dollar bill, then the generator has a win. Are we seeing that? And so we have two, two very opposite forces at work. One force is trying to pass data, counterfeit dollar bills as real. And the other force is the cop, the discriminator, is trying its level best to not mix up the real from the fake and to be able to do a good job at discriminating. And this process is called adversarial learning. It is very, very common actually. If you take an analogy from real life, when you play a game, let's say that you're playing lawn tennis, what is the best way for you to learn tennis? You would like to learn tennis by playing it against a friend, and as you play, you throw the ball at all sorts of places onto the court, hoping that your friend, your opponent, would not be on the field, would not be able to anticipate your move where you are next going to throw the ball, right? And let us say that you don't. You throw the ball in a corner. What does your friend then realize? That you tend to, he loses, but he realizes, or she realizes that, oh, well, you tend to throw balls into the corners of the court. And so your friend now becomes a bit smarter, is on the watch out for the next time that you may throw a ball into the corner ends of the court, right? And so is ready for that. So now you lost that opportunity, and now you try some other trick. And so gradually what happens is, as you and your friend keep playing with the goal of defeating each other, you both over time become better and better and better, right? And all the easy moves by which you could win against each other are gone because both of you have smartened up, right? And at the end, you see that it becomes a game of experts. And we see that when you see a World Cup match, or whatever those are called, Wimbledon and so on and so forth, of a tennis game, you notice that the two sides are fairly equally matched. They are playing a superb game. Like it's just a pleasure to watch, which is why you have spectatorship in perhaps hundreds of millions of viewers around the world of let's say, tennis match or a cricket match or a soccer or whatever it is, because it is it is the perfection that has been achieved by playing an adversarial game over thousands and thousands of games, and millions of moves and things have been learned and tried out, and their defense and offense have been tried out. So adversarial learning is all around us. This concept of min-max, sort of if I try to maximize the times that I can get the ball at a point on the other side in such a way that my opponent would not be able to field it, right? On the other hand, my opponent is making sure that they can always field it, but when they throw the ball onto our side of the court, we are not able to field it, right? And that is adversarial learning. And a very similar situation happens here in this kind of a situation where a generator and a discriminator, generator tries to produce fake bills, and the discriminator tries to tell a genuine dollar bill, apart from a fake dollar bill. And so gradually they both become very, very good. If they run it for a few million times, they become very good. Each time they learn a little bit, just the tiniest little bit. For example, if the generator produces a bird on a dollar bill and the discriminator says, aha, that's a total fake. And the generator then slightly changes the dollar bill, and the discriminator still says it's totally fake, but is a little less sure. Generator has found a little, just enough crack in the door to pursue that avenue and exploit it to see where it does it lead. And the beautiful thing is, in this game, if you play it sufficiently long, the generator can start producing very genuine dollar bills without ever having seen a dollar bill. Because now, through this process of learning, it learns, in effect, what dollar bills look like. Likewise, the discriminator, even if the discriminator had no idea what a dollar bill looks like, because it is given a dollar bill and told this is real, make a prediction. What is it? It makes a prediction and it may say whatever. It may say it is real or not. Probability of real is high or low. And then it is told the answer. It said, actually, that was real. Then the discriminator learns something from that exercise. So both discriminator and the generator, they gradually become smarter and smarter. And soon you reach a state at which they both become insanely good at it. They become like world class tennis players in a sense, right? If it were a tennis game, or the generator becomes world-class counterfeiter. But then you ask this question, now, what is the purpose of playing this sort of a silly game, right? Why would you want to make computers play this game, right? Or make AI play this game? And the answer to that is actually quite interesting. When the generator and the discriminator have become very good, then you can throw away the discriminator and you are left with the generator. And the generator can produce for you infinite variations of the dollar bill, each of them looking very, very, very realistic. Or for a check. Or as we saw in the last session, you could have train the generator and the discriminator to tell whether something is a human face. In the beginning, the generator might be drawing a brick or a house or a kangaroo, and the discriminator is immediately able to tell, well, no, that wouldn't do. That's not a face. But gradually, as the generator and the discriminator play this adversarial learning game, after huge number of rounds of learning on both sides, finally you'll get a really smart generator and a really smart discriminator. And if you remember, we went to this website. This person does not exist. And what did we see? We noticed that the process, the generator, was able to generate very, very realistic pictures of human faces, faces of people that simply did not exist. And then you realize that feels like magic. How does this generator produce, when you think about it, how does it produce such realistic human faces? The answer to that is it has been penalized for producing all sorts of things that don't look like a human face. And so it has learned from that. It has learned from the loss function. And that this combination of generator and discriminator, when you put them together, there is a word for it. This kind of an architecture, neural architecture, it has a name. It is called, and now the name would look very obvious to you. It is called, oh goodness, and let me pick another color. Generative adversarial networks. They are often abbreviated as GAN. Generative adversarial networks. So this is one network. This is a generative network. And this is the discriminative network. Right? And these two networks, they are playing an adversarial learning game with data. Right? And so this particular architecture was actually thought of in 2014. And here is how the story goes. And it was one of the pioneers in this field, Ian Goodfellow, apparently. So this is the story behind it. He apparently was at a pub and thinking that, see, in those days, we are talking about 2014. So let's rewind a little bit to see what those times look like. Around 2012 to 2014, there was a sudden sort of a quantum leap in the successes of deep learning or artificial intelligence. Um, for example, there was the so-called handwriting recognition. Handwriting recognition is important. People used to write on the envelope, and letters, for example, had to be sent across the country. If you could recognize the handwriting very accurately and convert it into, well, digital information, then the postal service could route your letters very effectively for or at least one important use case. And today, if you ever look at an envelope from your friend in which your friend has sent you a greeting card and the holiday seasons are coming, you'll often have friends who will write your name and address on the envelope and put a postage stamp and put it in the mailbox. If when you receive it, observe very carefully. At the very bottom of that envelope, you will notice little squiggly marks. Those little squiggly marks are actually the computerized encoding of your address. And what happens is that when you put your letter into a mailbox, the the postman collects all of that, puts it into a big sorting bin, and from there the computers take over. They recognize the handwriting, convert it into little text, and then from there onward, automatic sorting and routing machines take over, and your letters actually run. They're just routed to their transportation systems and everything, and we don't pause to think about it. But there was a time when letters cross country would take weeks to go through, and often letters were lost. People would write the same letter a couple of times over for it to go through. When I was growing up in India, it used to be pretty common for letters to take an extraordinarily long time to reach, especially if they were going 1,000 miles. But along the came these automatic routing and sorting algorithms, and then these algorithms that could detect human handwriting and convert it into an address, and then it would take over. And today, we sort of assume that if you write a letter within 10 days, it would cross the ends of the country. You can send a letter from here to Los Angeles, from here to New York, and probably in a week or 10 days, it will reach the other end. And letters rarely get lost. The so called dead letter problem has practically evaporated. Very, very rare to have a letter go to the wrong place or to no address at all. Right? It is not so common for that to happen anymore. So that is partly because of AI, partly because you have very good handwriting recognizers. But some of these developments, while LeanET, the initial handwriting recognition system that was deployed, and one of the grand successes of deep neural networks in artificial intelligence was adopted early on at the turn of the century. Much desired. There was a huge scope for improvement. So there was a grand challenge put uh, by the National Institute of Standards and Technology. They created a data set, which was a modified version of the data set is called the MNIST digits data set. It contained all sorts of handwritten, let's say, a digit. So human beings may have written 3 like this and 6 like this. Now, when you look at a 6 like this, it's a little hard to tell, is it a 6 or a 0, right? You may write 1 like this and you may write 7 like this, and it becomes a little hard to tell whether it's a 1 or a 7. So you have all sorts of examples, 4 written like this, right? And 4 written like this, and it's hard to tell whether it is a 9, right? And so on and so forth. Human handwriting has a wide variation. So they created a data set of about 60,000 handwritten letters or digits. And the idea was, it was a benchmark. Which algorithm could classify or recognize the digits best? Now, to know that a 3 is a 3 is a discriminative task. It is like a cop saying, I know what it is. It's a real bill. So when that was happening, the deep learning, there's a particular class of neural architectures called deep neural networks. They were having a renaissance. They were having a very, very good time, progress. And around 2012 to 2014, there was these advancements, one after the other, AlexNet, ResNet, and so forth. And they, in a very quick succession, they started beating the state of the art. And today, I mean, they already started achieving accuracy that surpassed human accuracy. Human accuracy is we get it wrong about 5 to 7% of the time. One of the great milestones was when neural networks could recognize digits even better than we could. Today, human beings are no match. We still are sitting at 5 to 7% error rate, but these AI algorithms, they are sitting at 99.9 something, 99% accuracy. Right? And the one areas where they don't do well are actually areas which, frankly, are not legit cases. They are so badly written that no human being can make head and tail of it. Right? But it is there, it's part of the data set. Right? So, in other words, the AI algorithms have achieved near perfection. And that was already happening around 2012 to 2014. And so, the question that people began to ask is the discriminative models, like this classifier, this recognizer of the digits, is doing so very well, but the generative models were lagging behind, relatively speaking. They were not having such a wonderful day, right? And so, the in a way, you can say that great great computer scientists and AI researchers like Ian Goodfellow were asking this question: can we somehow harness the power of the discriminator to create a better generator? Discriminators have become good, classifiers have become good. Can we harness that power to create a really powerful generator? And that is how it, and the story goes that Ian Goodfellow was sitting in a pub. He was slightly inebriated. Once a few beers down, we tend to be a little bit more optimistic, some of us. So he sat down and he began to let his imagination run wild. And apparently he came up with this idea that we could do this. He got very excited. He came back, and I'm told that he coded it up from in one of the in an interview that he gave on, I believe, the Lex Friedman show, a podcast. He said this is how the story is, that he literally coded it up in a couple of hours, and he was seeing results. All the people, all his fellow researchers sitting at the pub told him, this won't work, this is way too crazy. Right? You can't use a discriminator to train a generator. It doesn't make sense. There are many pitfalls in this, but he did it in a couple of hours, and then the rest is history. Obviously, by the time the paper came out, you will see that there are many authors to the paper. They all contributed in implementing it, testing it out, making things happen, and so on and so forth. But this is how great ideas like this came. And I would say this, for generative AI, this was a very big milestone, because it, for better or for worse, it was great. Out of this generative adversarial networks came the ability to do, like we saw 2 days ago, to do neural style transfer. For example, you could write, or you could transfer Van Gogh style to your photograph, right? Easily, and create a fake Van Gogh of your scene. There are many good uses of that generative style, excuse me, neural transfer. You could do data generation. You could use it for medical diagnostics. A lot of it. There are many, many use cases that we talked about the last time. I'm not going to rehash it, but it has generative adversarial networks have had a transformative effect on the world itself, not just AI. But not all for the good. It also unleashed the world of fake images. For example, now fake images may not be that harmful, but it can be. So, for example, today, in one of the most startling demonstrations of this was at MIT. I forget the year. I would like to say it was 2018 or 2020. Uh, the professor started the course on artificial intelligence by saying we have a special guest to introduce the course. And that special guest, it turns out, was Barack Obama, who on the video gave a very good introduction to the course. And then, and it was very realistic. Barack Obama's voice, Barack Obama's gestures, his facial expressions, his accent, everything was captured. And then the professor mentioned that this was actually not Barack Obama. It was him speaking with Barack Obama's style of speaking, his voice, his mannerisms, his gesticulation, as his Barack Obama's identity imposed upon the content that the professor was speaking, or I think it was one of his graduate students who was speaking, a teaching assistant who was speaking. Right? Now, why that is a most shocking and powerful demonstrations of the power of generative AI or of GANs, you realize that it also unleashes the potential for great mischief. Today, we can take a couple of minutes of your recording. I can take just a few seconds of your voice and then have a voice recording of you saying whatever content I give. And all your friends and family will attest to the fact that it was you who said it. They hear you, even though it was not you. You can generate fake videos and so forth. So the other side of generative AI always is the potential for abuse or the possible in what uh, some people have called very evocatively a possible collapse of reality, a complete blurring of the boundary between what is fake and real. And if you think about it, that is the entire architecture of a generative adversarial network. The generator tries its best to blur the boundary between what it produces and what is genuine. And when it succeeds, it succeeds spectacularly. So, what I would like to do is, I would like to, in the last 15 minutes, give you a more realistic picture of how this happens. I told you that it tries to figure out what does the reality look like. Now, I will use a small bridge, and this may get a little bit technical to understand what it is about. Suppose data, real data, is circular. Let's say that it is like this. This is the real data. In other words, all the real data could be represented as in a page. If you draw it out, a two-dimensional data in a page, they are all limited to this circle or a band or a ring. All the data belongs to a ring. Anything outside is wrong. This is wrong. This is not the true data. This is not data. These are not data. But the only thing that is real data are points here in this ring, yellow ring. This is the reality. So this is the real data, real data. Now imagine that you have a generator which is trying to take an input. What it will do is, it will basically imagine that it gets data. Let's, for the sake of argument, imagine that it gets a page. Oops, sorry. It gets a page and it can take points somewhere here. What does it need to do? It needs to somehow fold these points into such a way that it only produces points that belong to the yellow band. Produce a point from the yellow band. Because if it does that, if I produce, so let's take a point, an orange point. Now, let me take a color that would stand out. Let's say this color. What color would stand out? Okay, let's try a luck with this color. Right? Do you see this big violet dot here on the screen? If the generator could produce that generator could produce this point, you would realize that that point is as legitimate as it could be. It is very, very hard to tell it apart from a fake, tell it apart from a real point, isn't it? Because it belongs to the band or the yellow ring band of real points. Are we together? So in a way, the goal of the generator is to discover the data distribution. And that is the statement made mathematically, that generative models, they discover the actual distribution of the data, the complete distribution. How is the data distributed in space? Because if the generator can discover that, what is realistic data looking like, then it can produce infinite samples of realistic looking data. Or more poetically, it can produce infinitely many faces that all look real. Do you see that, guys? So this idea, I would like to show you with a real lab example. At this particular moment, give me a moment to do that. I am going to do it here. So let's look at this. If you folks are able to see my screen, I'm going to show you a fun thing. I just took this circle. Let us say that the reality is like this. The real data are the green data points. What we are going to do is we are going to take one step of the generator, and the generator has produced this data here, right? This sort of a data. Now, a sample. You see, generator is producing data points here. I don't know if you guys are able to see my mouse. It's producing data. Actually, this is too. It's producing data here. But this data, if you look at the discriminator says, well, a discriminator also doesn't know where the real data is and where it is not. So if you look at this box or this big box, discriminator is saying maybe real data is everywhere. So the cop is confused, doesn't quite know. And so we will let both of them make a step. And what happens is that and you can keep on making steps. What happens is that the discriminator is noticing that, the generator is noticing that discriminator tends to give higher truth values or trust data on the right hand side of this box. Right? Do you notice that this is darker green? And so what the generator does, the fake data maker does, it is trying to push the data in this direction towards the dark green areas. Do you notice that these points have a tail to them? And all of those tails point towards the direction of the dark green. Right? And so let's go a few steps, and you notice that it is chasing it. And for some reason, the discriminator is feeling that, oh my God, fake is coming from behind. So it is putting its stress more and more onto the boundary of this page. And what does the generator do? The crook do? It tries to produce data closer and closer towards where the generator has trust. And now notice that something very interesting has happened. The generator doesn't trust data coming from here because it has figured out that that is where the fake data used to hide. And the generator has a lot of trust data in the data, dark green, on data in this area of the page. And so the generator, the fake data maker, is trying to capitalize or exploit the belief system of the discriminator, of the cop. And so we will do this. And you notice something very interesting. So I'll let this thing run itself out for a few more epochs. And if you notice the loss function of this, the generator is having a pretty good loss and the discriminator loss is decreasing. Do you notice that the discriminator at this moment is doing pretty well? The loss is decreasing means it is beginning to figure out what game it needs to play to win against the cop, right? And the discriminator, the cop, is having a rather bad day. Its losses are increasing. So let's continue this a little bit more. And by now, the discriminator, the generator loss is beginning to climb up. The discriminator is picking up. I'll just let it run for a few epochs. And you see how they go about trying to fool each other. But at the end of it, observe, and I'll just put the generator thing also here. This colored, this purple is what the generator believes it is producing. And do you notice how the purple thing is now beginning to overlap the real shape of the data? And we have gone through 900 epochs. 900 epochs means, and let's say that there are 100 points, it's almost like 900,000 times or 1,000,000 times it has learned. Both of these guys have made little efforts to learn against each other in the adversarial game. And it sort of continues quite a bit. And by now you see, if you were to see it, it is producing pretty realistic points. If you notice this, what the generator is producing are pretty realistic points are coming through. And we can let this game go through for a few thousand rounds, and then you'll soon notice that discriminator and the generator, they begin to converge. They begin to get pretty good at this game. After a little while, you'll realize that the generator, the discriminator would be somewhat at a loss. Its loss of the discriminator stabilizes, whereas the generator tends to do better and better and better after some time. Now, I will just stop here because I think it is pretty obvious what is happening. If you look at the shape here, let's look at the shape. Look at this shape here. When you look at this shape, you pretty much get the sense that the generator has figured out how to generate fakes. It is still making mistakes. It is producing some data points in the center, which the discriminator can tell and say, hey, that's fake. But still, the generator is doing a pretty good job. And even if you stop here, you would agree that the generator would be able to produce predominantly realistic data points, isn't it? And that, folks, is generative AI, right? In a very visual way, that is generative AI. That's GAN's one of the first powerful, very successful. There were many generative algorithms, as I talked about, since the 1980s, but this one really caught people's imagination. And you can say to some extent that the gold rush or the renaissance of this sort of generative AI started in 2014 with algorithms like this. The other algorithm that is similar to this is that of autoencoders, variational autoencoders, which I will keep perhaps for another session. Actually, when I do the actual course, which is a more in-depth course, a 7-week course, we go far deeper. We do a lot of lab exercises and coding exercises, and we go into the mathematical theory of all of this generative AI. In other words, it's a full formal course. There, when you do that, you will encounter these things at a much greater detail. But this one, because it is this particular sequence, because it's meant for a much broader general audience, I'm a bit hesitant going in deeper into it. And so with that, our hour is almost up. I would like to take another example. Let's take this example. These 3 clusters of points are the real points. And I will just let the system run and see how well it does. You look at this, the fake data is the generator is having all sorts of theories of what the real data probably looks like. And sometimes it is grossly wrong. Like at this moment, it's grossly wrong. And it is trying to make head and tail of it. And it's having a pretty bad job of it. So I must stop it here. Or let me run it a little bit. Yeah, I'll stop here. Do you notice that at this, well, in this particular case, there are points in between which are totally fake, but the realistic points that it is producing belongs to just one cluster, right? Actually, let me rewind it and play it again, because it's a problem that used to be there in the early GANs, but we have found a way to solve it. Yes, I'll stop here. Do you notice that all of these points are near this one cluster, right? And it gets a little bit better, but let's run it a little bit longer. I'll stop here. Well, one step back. I wish I could do one step back. Okay, I'll let it run a little bit more. Yeah, I'll stop here. So did you notice that all the points that it is generating is near this cluster, the generator? It's somewhat like, the generator has figured out how to write the digit 3, and it had a pretty good success. So it reinforces itself, it doubles down on that and says, let me write all sorts of fake 3s, but it is not producing other digits. Right? That is called mode collapse. When it pretty early on figures out that, hey, I hit the jackpot. I produced something, a shape that fooled the discriminator. Let me produce lots of these sorts of shape. Right? And then it doesn't produce anything else except 3s. It used to be a common problem in the early GANs, but today we know how to solve it. And when you actually do the course with me and you do the lab exercises, you will learn about all of those techniques, practical techniques to prevent a mode collapse. So the last thing you want to do is when you're told to produce all sorts of human faces, the only thing you produce is the face of 5-year-old boy, lots of them. So soon people would know that the easiest way is, if it is not a 5-year-old boy, it's probably genuine. But if it is a 5-year-old boy, then maybe there is a chance of it being fake. Right? So that would be no good as a generator. It doesn't cover, in other words, the space of all realistic examples. And that has a lot of practical implications in terms of generative AI. So I will stop here, right? And I will take questions now from the audience.
Thank you, Asif. We have a lot of questions in the chat. We'll start with that. And if any one of you have a question, please raise your hand through the reactions button on the bottom of your screen. So let's start with the first question from Ramki. What if the discriminator produces only Boolean output, match or no match?
You don't do that, Ramki. See, the nature of machine learning is, and remember, so since you are Ramki, you are mathematically trained. So I will take the liberty of bringing in the mathematical notation. See, you need a loss function, and you need to be able to take the derivative of a loss function. You can take the derivative only of continuous differentiable functions, right? So the discriminator must produce a probability distribution, must produce P, which is a continuous differentiable function of the input. Are we together? And if you can, by its very nature, it's not a Boolean, it's not a true false. But we often categorize it as a Boolean by saying, if the probability is more than 50%, it is real. If the probability is less than 50%, it is fake. Right? So by thresholding the value of the probability, you make it into a Boolean or a binary answer, true, false answer, fake or real answer. But you make the machine produce a continuous differentiable function because you have to take its gradient, and you need the gradient to do gradient descent and the back propagation, which are the pillars of neural networks. Does that answer your question, Ramki?
Okay, we'll go to the next question. Thank you, Asif. So the next question from Jeevan, when do we know when to stop these iterations in the context of the training that you're initially
Oh,
showing?
yeah, excellent question. Let me show you in a realistic way. See, you notice that here, look at the top corner here, the loss functions. Right? When the loss function begins to stabilize and you don't see any further improvement, the loss or the, so for example, this is the metric, I believe the accuracy metric or whatever. Once you stop seeing improvement in that, then you know that it's time to stop. In practical terms, that's the best way to do that. You reach a point of diminishing returns. The generator and the discriminator become extremely good, right? So think about it for athletes, or painters or musicians. At the end of the day, great world-class musicians. By the way, this was one of the lessons in that book, Outliers. They practice 10 to 14 hours a day, day after day after day. But at some point, you have to say, you have reached a saturation point. These people have become world class musicians, right? So it is somewhat like that with the generator. At some point, the generator becomes a champion faker. It generates, well, I wouldn't use the word fake in a derogatory way. I would say it generates realistic data points, things that mimics reality to a very high degree of fidelity. And at that point, your purpose is served because what do you want to do? You want to use it for some real value thing. For example, you may be generating data for downstream experiments, right? Downstream tasks and so forth. And by the way, in data generation, especially in domains where data is hard to generate, is one of the excellent and great use cases of the GANs and the generative AI.
Thanks, Asif. We'll go to the next question in the chat and then we'll come back to the hands. Gopi has a question. Is the real samples equally random, or is there an approach to introducing a real samples from a pile of currency to speed up the learning? Does that show any bias in learning? So it was primarily with the example of currency faking.
Yeah, people have asked this question, but the answer these days is you want to randomize both the input data, right? You don't want it to. You don't get anything by having a particular order or sequentiality to the, like you don't want to serve only $1 bills, wait for the discriminate for the generator to catch on to $1 bills and then introduce the $100 bills. It isn't like that. You just completely randomize it, and then you randomly to the discriminator, you either give it a fake data or you give it the real data and ask, is it real or is it fake? Or if you look at the MNIST data set, what you want to do is mix up all those 10 digits, zeros and instances of those, the real ones, and have the generator figure out what those 10 digits from 0 to 9 look like. You don't bring in any order, specific order.
Thank you, Asif. We'll go to the next question from Anshu. Can you please unmute yourself and ask the question?
Yeah, hi, Asif. Thanks for this excellent course. Uh, what if the discriminator was smart enough, figures out that the generator is pushing fake data, and just like the generator is getting smart and pushing data, it says, I'm going to either give him fake feedback so that it doesn't get any more information from me and doesn't learn any more from me.
Yeah. So, Anshu, first of all, there are two parts to your question. One is, what if the discriminator becomes pretty smart? And the second part is, what if it starts not giving information to the generator? No, you prevent that. But in the way you set up your two neural networks, you don't let the discriminator hide information from the generator. In other words, the back propagation of the loss is equally served to the generator and the discriminator. They both get a chance to learn from it. it's the way you set up the whole algorithm. The first part is, what if the discriminator becomes pretty smart early on? In fact, that was the problem. Early on, what happened is, if the discriminator is pretty good, you tend to see more collapse. Like, like in this particular case. So here itself, there is somewhere a knob which we can turn. Let's see where it is. By which model graph. Yeah, see here. What you can do is, suppose you notice that the learning rate of the generator is a little bit more than the learning rate of the discriminator. If
Right.
you make the learning rate, if you make the discriminator way smarter, the generator gets into trouble actually. So for example, if I make this Adam, let's see if this happens in this particular case or not. And it has, okay, so this has a pretty good learning. Let me reset it and let's see what happens. No, sorry, I'll stop it and this. And let's try this. You realize that the generator is sort of struggling, bouncing all over the place, and it has a tougher time
Got it.
to get to an answer. So one of the things that people did, they learned early on, is that, see, the discriminator has one edge, one advantage. It actually is told it knows, it gets to see the real data. The generator never gets to see the real data. It's almost like generator never sees the actual digits or what it looks like, or never sees the dollar bill, but the discriminator does. So there, so a lot of, over the years, people have found ways to slightly cripple the discriminator so that it doesn't have too much of a lead over the generator.
Okay. Thank you.
Thank you, Asif. Thanks, Anshu. We'll take the next hand. Alicia, if you could unmute yourself and ask the question.
Well, supposedly, a member of my family has recommended me just to start.
Could you please say it a bit louder, Alicia? Unfortunately, I'm having a bit of difficulty hearing you.
Can you hear now?
Oh yes, now I can hear you loud and clear.
I'll go straight to the point. I have just thought an idea. Is there a possibility to have the generator and the discriminator go hand in glove just to cheat humans? And I'm engaged in songwriting. Well, when no, let's say, well, I live in Argentina. Sometimes it's quite challenging when I have my mind set to write and all this. When, for example, the creative process and when we have the generator and the discriminator working together, perhaps at a certain point they stop because they are like kind of overwhelmed by too much data, and they say, well, no, I stop this and I leave this, I put it in this box, and I set this aside for a later time, and I'll continue with another task that the operator provides me with. And then he gain in the meantime, she, well, it gets more knowledge, more experience, and just grab this pending issue, like and it says, oh, it's piece of cake now. How can we, let's say, try to uh, mm, follow the interaction and try to get lessons learned, how to, let's say, oil this process.
Yes.
I don't know if I explained this the right way. It's like it just occurred to me, and I because I think that if they start to work hand in glove, it would bring some. They may cheat us, perhaps, might in the long run.
Yes, Alicia, that's a very good thought. Now, today we do worry about those things, not about this particular simple neural architecture, But with the various AI agents that we are creating, there is a lurking fear amongst us humans that what if we ask them to do one thing, but they collude and do something entirely different? And those concerns are completely legitimate, or they learn in a way different from the way we ask them to learn. But for this particular thing that I mentioned, the generative adversarial network, these are very simple networks. They don't have any free will, or ability to reason or make decisions like that. They're forced into learning together.
Uh-huh. Uh-huh. I see. I see. Okay, thank you. Thank you so much. Anyway, I'd like to connect with you later in the year perhaps
Sure,
when I'm more, yeah, thank you so much for your generosity and your time.
of course.
Thank you for the question. Thank you, Asif. We'll go to the next question from Gopi. Can you explain your statement on how the generator leverages the power of discriminator as the essence of generative AI?
That's a very good question. See, the idea that Ian Goodfellow and these people had is they said, see, the discriminators have become very good, right? So if the discriminator can tell whether this is a fake bill or a real bill, why can't we use that to teach the generator through an algorithm called backpropagation, but basically use that to force the discriminator, in a sense, to teach the generator. And that is the gist of it, the min-max game. It is like, if you want to learn tennis, you surely want to learn by playing it against a person who is stronger than you. Because if you play tennis against a person who is far weaker than you, there is no way you are going to improve. The only way you are going to improve is if you're playing against somebody who's a bit better than you, right? Or maybe quite a bit better than you. And you have to somehow figure out a way to thrive and survive. And that was the main idea of this adversarial network, that discriminator is the person the generator is playing tennis with to learn and get better. That's the gist of it. You're playing an adversarial game, just like tennis is an adversarial game. And to play an adversarial game, you want a worthy adversary, otherwise it's no fun.
Thank you. As a follow-up question, Gopi was asking, what is that element in the generator that is able to show the direction to migrate in that simulation?
Oh, so that is the gradient, the direction in which it realizes that. See, what happens is, so it gets a little technical, but let me explain that. You mean those arrows, those tails that these points had?
Yeah.
What it means is that, see, when you have the loss, the generator is looking at the loss function, and the gradient of the loss tells it that in that direction, if I move, then the it will look less fake. It is mathematics, basically. The gradient of the loss for the generator points in that direction. Right? Actually, it's the opposite direction, specifically. The gradient of the loss points in the direction in which you should move away from, but if you take its negative, it points in the direction that you want to go to, if you want to be a slightly less fake, a little bit more realistic. And that's one of the beautiful things about mathematics, that just the gradient. See, gradient is, if I may just give you a poetic example. Today, when you go from place to place, you use the Google Maps or some maps, Apple Maps or whatever it is that you use. You use a navigation system and a GPS. It turns out, in a way, in a metaphorical way of speaking, in the world of calculus, in the world of functions, there was always a map, a navigator built in. If you wanted to go in the direction in which a function increases, you just apply a mathematical operation called the gradient, the derivative. The moment you take the derivative of a function, a multi-variable, it would always point in the direction where the function increases. So if you keep on following that, you'll get to the hilltop of that function. And if you follow against that, you'll come to the valley of the function, the bottom where the function minimizes. And so, in a way, you can say that the world of functions, they come with a built-in navigator. They give you an idea in which direction it increases and decreases. And that is what the generator is using.
Thank you. We'll go to the next question from Inder. How does these GAN models useful in the context of something like ChatGPT, just trying to connect the dots?
See, ChatGPT is a pure generative model. When it generates, there's a lot that, see, ChatGPT, for example, is not one model. And obviously the architecture has never been revealed publicly, but to the best of our knowledge, it is a multitude of experts. There are at least a dozen to 2 dozen independent GPT 3.5 models and many, many other things that have gone into it to create a generative effect. Now, I give GAN as the easiest one because its architecture is easy to explain. In the coming week, I will be talking about so-called transformers. Those GPTs, they belong to a class of transformers which emphasize the so-called the decoder half of the transformer much more, the generative half of that much more. And how they do it, we will talk about it. So you could say that the Chat GPT's architect, well, not Chat GPT, GPT's architecture is slightly different. What Chat GPT's architecture internally is, or how many pieces it is made up of, no one knows. Only OpenAI knows, and they have been pretty secretive about it. But all we know is that it is not one model, it is a whole constellation of models that they use.
Thank you. We'll go to the next question from Mahesh. How do you balance the bias between the generator and the discriminator?
See, the goal of these systems is to create a very good generator. So you do everything in the system possible to favor the generator, to give it the advantage. Because at the end of it, you'll throw the discriminator away and use the generator for most situations. So you cripple the discriminator, you do techniques. And by the way, there's this beautiful thing called vector arithmetic that you can apply. After some time, if you figure out that if you give this input, it produces a person with a clean-shaved face. And if you give this input, it produces a face in the latent space. It produces a face that is that of a bearded person. So now what can you do? You know that if I want to go from a person to a bearded person, all I need to do is traverse the path between these two vectors, go along the direction that goes from the one vector to the other. Because gradually, and it's really amazing to see that, you can see a beardless, a well-shaven person gradually transform into more and more and more beards till the person looks completely bearded. Or to go from a man to a woman, or to go change the age of a person, to go from a child to an old person, middle-aged person. So you can do all of these vector, smooth transformations after a little while, once you create very good generators. So look into the work, for example, of style GANs and so forth, and conditional GANs. The whole field of GANs is become a whole field of generative AI. And it can do amazing things. So you remember that there was a time when you would sit in like if you are a witness to a crime and the cops would make you sit with an artist and say, okay, tell me what did the fellow look like? And no matter how well you described, the artist would come up with a face that could fit just about anybody. Like it barely, it was not quite close to the real deal. But imagine what generative AI can do. You can today, and this is one of the things actually we do in the workshop, the course, or we convert textual descriptions to realistic faces that match that. And then if you say that, no, a little bit more mustache, a little bit wider face, as you say it, the faces transform. They change. So that you end up with, in a couple of minutes, you can end up with a face exactly like the person you saw. Right? Or very close to the person that you saw. And imagine what it does. What's a new world that you're looking at?
Thank you, Asif. That actually answers the next question from Rajan. So you pretty much cleared 2 questions in the chat. We'll go to the next one. Can you please talk a bit about vector databases and feature stores in relation to this example? I think we're going to cover that in our next session, so I'll probably pass that. Would you say that generative AI uses patterns from the discriminative data? It's a question from Dr. Brown.
Yes and no. See, the purpose here is not to make the discriminator a really good discriminator, though that is one of the effects of training again. That discriminator also smartens up. But generally, you find more efficient ways to create very good discriminators. You use it mostly, the end goal is mostly to come up with a really good generator, right? So you don't really, there is a bit of work, there is a bit of body of research that says, could we not use GANs or this sort of an approach to, in itself, create much smarter discriminators, much smarter that. I don't think there is a vast amount of literature. There is some body of research that has successfully done that.
Thank
But
you. Last question, and then we'll conclude the session. This one is from Jeevan. Is generative AI is equal to a predictive AI?
roughly, see, here is the thing. I would say it is sampling of a probability distribution. What do I mean by that cryptic statement? Let's go back to this. See, when you figure out that your data is around this yellow band, you have created a probability distribution of the data in the language. And so you could you could sample off this distribution. You could, in other words, pick points in the yellow band, and they would all look realistic and they would be the data. So that is, therefore, generative presupposes understanding of a probability distribution or a predictive model. Then only can you generate. That is part one. Another way to look at it is, if you're thinking these days, people often look at LLMs, ChatGPT, etc., and they say, when I ask a question, how is it able to generate an answer? Is there a prediction going on? The answer is yes. What it does is, it produces the problem. It says, what should be the first word of my answer? So in a vocabulary of 30,000 words of English, let's say, which of the words should I start with to answer this user's question? Right? It will pick a word that is most probable. Now, in that word, in that probability distribution, itself be a sample of it. You don't necessarily pick the most probable word. Experience shows that if you do it, you tend to be very repetitive and bland. So you, for variety, you take either the most probable or the next most probable, excuse me, or some sequence of words along that, high probability words. And it has to do with temperature. It has to do with, by the way, these things I'll talk about in my very next session. But at the, so before every, these LLMs are next word predictors. They just predict the next word, and then they ask, okay, what should be the next word that I should predict? And the next token, and the next token, and the next token. But those tokens are all taken from a probability distribution. A probability distribution is a prediction, and therefore you can say, in a very realistic sense, that all generators presuppose the construction of a probability distribution, and therefore are predictive in nature.
Thank you. We have two more questions, but I think we'll make it quick. Are generators and discriminators sort of a parallel to the blue and red teams in a cybersecurity field? I think it's a good analogy.
Yeah, that is a good analogy. It's an adversarial game wherever, see, adversarial learning is one of the most effective forms of learning.
Yeah, excellent analogy, actually. I loved it. The last question, generative AI is focused on creating new content from images to music, while predictive AI leverages historical data for future trend forecasting. Is that a true statement?
Not really. See, predictive is just to create, see, there are two aspects to it. I think what you're trying to tell is to predict based on past data. Those are discriminative models. predictive models are a large class. Okay, if you want the specific technical detail, it is something like this. If I'm predicting whether it's a cat, given the input attributes of the animal, that it has a mustache, that it has two eyes, is it a cat or a horse? Right? This is a discriminative model, and its job is to predict based on the learning from a lot of training data, which is historical. So to that extent, yes, this is one class of predictive models. The second aspect of predictive models is you learn the entire distribution of animals and their attributes together, right? In a feature space like weight, etc., etc. What do these things look like? And then when you sample off it, you just randomly take a point in that space, a likely point in that space. That point may not exist. So yes, you have learned from historical data, even for generative models, because it is the past that informs you, the data that informs you. But at the end of it, whether you build a discriminative model or you build a generative model, that is your choice. And it depends on the purpose you're going to use it for.
Thank you very much, Dr. Asif, and thank you everyone for joining. We will conclude today's session. We'll look forward to seeing you on next Tuesday. Please make sure you follow us on LinkedIn, and if you have any questions or any further future guidance that's required, or you're looking for it, please reach out to me at madhu@supportvectors.com or info@supportvectors.com. So thanks a lot. Have a wonderful rest of the day, rest of the evening, and take care.